Hello all, welcome to the video lecture. I'm Ramesh Lama. In this video, we'll be discussing about the transfer learning. As we know that the large and effective deep learning models are data hungry. The training time and the amount of data required for such system or models are much more higher than that of the traditional machine learning systems. And they require training with the thousands or even millions of data points. However, when the number of data points available for the particular task that we are interested in is very low, for instance, we are trying to determine the species of the bats, but we don't have enough data, or we are trying to diagnose chest X-ray and the image data set available is not enough to train the deep learning model. In such scenario, we go for the transfer learning. In transfer learning, what we do is we pre-train a convolutional neural network or the model on a very large data set. For example, ImageNet data set which contains 1.2 millions of images and 1,000 categories, and use the pre-trained weights either as an initializer or fixed feature extractor for the task of interest. Here we can modify classification layer from 1,000 neurons to the number of classes in our new data set and then train the network. These pre-trained weights are the basis of transfer learning. And there are various models with the state-of-art performance that have been developed and tested across the domains such as computer vision and natural language processing (NLP). And we are lucky that many pre-trained architectures are directly available. And there are three major scenarios for transfer learning, which are as follows. Or we can say the ways to use the pre-trained model. And one is the feature extraction. Here what we do is we use the pre-trained model as feature extraction mechanism. We remove the output layer and use entire network as the fixed feature extractor for the new data set. For instance, we take the model like pre-trained on the ImageNet and remove the last fully connected layer, then treat the rest of the model as a feature extractor for the new data set. And as we know, in an AlexNet, this would compute 4006 vector for every image that contains the activation of the hidden layer immediately before the classifier. We call these features as CNN codes. Once we extract the 4006 codes for all images, we train a linear classifier. For example, we train linear SVM or softmax classifier for the new data set. And another one is the fine-tuning the model. It is the second strategy is not only to replace and retrain the classifier on the top of the model on the new data set, but to also fine-tune the weights of the pre-trained network by continuing the backpropagation. We use the pre-trained model partially. Here we use the pre-trained model partially. We keep the weights of the initial layers of the model frozen while retrain the higher layers. And it is possible to fine-tune all the layers of the network, or it's possible to keep some of the earlier layers fixed due to overfitting concerns, and only fine tune some higher level of the portion of the network. This is motivated by the observation that earlier features of the network contain more generic features. For example, edge detectors or color blob detectors that should be useful to many tasks, but later layers of the network becomes progressively more specific to the details of the classes contained in the original dataset. In case of ImageNet, for example, which contains many dog breeds, a significant portion of the representational power of the network may be devoted to the features that are specific to differentiating the dog breeds. So another way to use the pre-trained model is use the architecture of the pre-trained model. Here we only use the architecture of the model. What we do here is we initialize all the weights randomly and train the model according to our the data set again. And while we're talking about the pre-trained model selection, the question arises: how can we decide what type of transfer learning we should perform on our new data set? And the selection of the pre-trained model is a function of several factors. However, we consider two factors, which are the size of the new data set and the similarity of the original data set with respect original data set with our new data set or the target data set. Like the size of the new data set may be small or big. Like we train, as we have trained, we have pre-trained the model, the pre-trained model on the big data set like ImageNet. But the new data set may be bigger, same as the pre-trained model, or it may be smaller, and its similarity to the original data set, like the ImageNet, like in terms of the content of the image and the classes are very different, such as the microscopic images. And keeping in the mind that deep CNN features are more generic in the earlier layers and more original data set is, and more original data set is specific in the later layers, here are some common rules of the thumb for navigating four major scenarios. Means there are four major scenarios based on the size of the data set and its similarity to the original data set. We will see one by one here. Like one scenario is when the new data set is small and similar to the original data set. In this case, as we have seen in our previous slide, like we can use it as a feature detector. What you can do is we can use the pre-trained model as just as a feature detector. Since the data similarity is very high, we do not need to retrain the model, and the data as the data is similar to the original data, we expect higher level features in the model to be relevant to this data set as well, like the relevance that the higher level features of original data set and the new data set are relevant, or they are almost we can say they are somehow similar, or they are relevant to each other. So in this case, the best idea is to train the linear classifier on the CNN codes or the features that we extract. So all we need to do is customize and modify the output layers according to the problem statement, and we use the pre-trained model as a feature extractor and train a new shallow model on these features. We can see here this is our pre-trained model, and we have here that the output layer consists of the 1000 neurons, and what we can do here is we change these output neurons, these 1000 neurons, to like we replace this with some shallow classifier or some linear neural network or linear classifier. And what we have here is we have the target data set, which is similar to the similarity is high with the original data set. And what we do is we use this pre-trained model as a feature extractor, and once we get the features, then we use these features to train the shallow classifier, and this shallow classifier is designed according to the new data set. And the key idea here is we just leverage the pre-trained model's weighted layers to extract the features, but not to update the weights of the model's layer. We don't update, we just keep those pre-trained models weighted layers fixed and use it for the future extraction during the training of new data for the new task. And another scenario is when the new data set is small but very different from the original data set. Since the data is small, it's likely that it is likely best to only train the linear classifier. But as the data is very different, it might not be best to train the classifier from the top of the network, which contains more data specific features. So what we do is instead we might work better to train the SVM classifier or some new classifier from the activations somewhere earlier in the network. And we can in this case we can also freeze some of the initial layers, let's say k layers of the pre-trained model, and then train the remaining n-k layers again, or we can say that fine-tune those remaining layers, and that is the initial layers are kept pre-trained or unchanged, which have been trained on the last data set previously. And we can try and test as how many layers to be frozen or how many layers to be trained. Like we can see here, this is our pre-trained model. Here in the transport learning, what we do is we keep the upper layers we keep some of the initial layers frozen, and we fine-tune the upper layers, or we can these fine-tuned layers can be from the earlier layers, or we can increase, or we can change the number of layers to be fine-tuned or to keep frozen is based on the data. Like if the target data set is very small, then what we can do is we keep most of the layers frozen, but as the number of target data set increases, and we can fine tune, like we can increase the number of fine tuned layers, and the most important thing here is like we can see that the target data set is completely different from the original data set. Like we can see here, these are the images that we encounter in our daily life, like dog, and here the target data set is from the some medical imaging, or we can say like this is the chest x-ray. And when another scenario is the size of data set is larger, however the data similarity is very low. Like here we have got the target, like the data set, the new data set is large, and what we can do here is we can train, like as we have larger data set, our neural network training would be effective. However, since the data we have is very different from as compared to the data set used for the training our pre-trained models, the prediction made using the pre-trained model would not be effective. So it's best to train the network from the scratch according to our data. So in this case, we just use the architecture. We can train the neural network from the scratch according to our data. So no more use of the pre-trained parameters or weights we don't use any more weights from the pre-trained network. And another scenario is size of data is large as well as there is high data similarity, and this is the ideal situation. In this case, the pre-trained model should be most effective. The best way to use the model is to retain the architecture of the model and initial weights of the model, and then we retrain the model using weights as initialized in the pre-trained model, or we can see this as a fine-tune through the full network. What we do is we pre-train the model with our original ImageNet data set. Like with the original data set, we we pre-train, and as our Tiger database is similar to the similarity is high with the original data set, what we do is we use the we pretend weight as the initial weights, and then we fine-tune the whole network, or we retrain the whole network with our new data set. And the many state-of-art deep learning architectures have been openly shared by their respective teams, and these span across different domains such as computer vision and the natural language processing, which are the most popular domains for deep learning applications. And pre-trained models are usually shared in the form of millions of parameters, or the weights the model achieved while being trained to a stable state. And the pre-trained models are available for everyone to use through the different means. And the famous deep learning Python library Keras provides the interface to download some of the popular models, and we can also access pre-trained models from the web, since most of them have been open sourced. And these are some of the pre-trained models which are available, like including BGG16, BGG19, Inception, B3, Exceptions, ResNet 50, and AlexNet. And these are the pre-trained models that we can use. And this is all about the transport learning, and we will see on the next video.